In this video, we'll look at fracture mechanics. Alright, it's closely linked to l2v6 of this playlist, talking about brittle, ductile. Alright, just a brief talk about it within that video. But what we're going to talk now is actually dealing with brittleness. And brittleness, in such of the case, will deal with some form of cracks. Alright, so how do we so-called touch on this issue is that what is the allowable crack length such that when you apply two forces, alright, it will not propagate, it will not become bigger. Alright, what is that particular crack length that we're actually trying to find? Alright, because if you were to load it with a very little force, alright, this crack may actually will not actually propagate. Alright, but however, if you were to pull it in such a way that the stress load is so high that it will propagate this thing. So therefore, we're actually trying to look at what is the actual acceptable length, such that when you pull this thing with a applied force or stress, you will not actually propagate it. And therefore, how do we start? Therefore, in this example, we will talk about the concept of the principal stress, of how to apply in this situation, and also the concept of using invariant to find this principal stress. And therefore, also that we will introduce you to the understanding of fracture toughness. How do we apply all this in? Alright, and therefore to start, understand what is the fracture toughness of this material. Alright, so perhaps in this, so therefore we will start off with an example to do it out. So for example, we have a fracture toughness of a ceramic. This is the material given by this is the fracture toughness, is equals to the principal stress 1 multiplied by pi times the area. Alright, I believe. Sorry, the length. Okay, the length. Sorry, this is the crack length. Crack length is A. Alright, meaning fracture toughness is simply a certain force, sigma 1, with the greatest force of the principal stress, if you remember. This is the principal stress over here. This is the largest stress you could get. This is the lowest stress you can get, and this one is a tensile stress, and this is the compressive stress, and sigma 2 is simply the in between. Alright, talk about it. And therefore, to talk about the tensile stress and the largest stress, you're going to talk about this portion over here, trying to actually pull this or rip this crack apart, things like that. And therefore, we talk about sigma 1 as this portion over here. Alright, multiply by some equation, square root pi times within itself is a crack length A. Alright, it's not an area, so please be careful. And therefore, this also lays down the understanding that this dude over here, you must remember. Alright, you need to know that when we talk about cracks, you're going to talk about fracture toughness, then you're going to talk about this equation. Alright, so therefore you need to take note of this. The fracture toughness is simply 24 MPa square root m. Alright, square meter, I would say. And so far I've been talking about fracture toughness. Then what exactly is fracture toughness then? And to my best knowledge, is within this range. Alright, it's within the yield stress to the ultimate stress. Alright, it's within this range. So this thing, if you remember, this thing is actually a plastic behavior, but actually deformed permanently. So therefore, crack itself is also deformed permanently, right? So therefore, this is the touching on the fracture toughness part in terms of the stress strain curve. And I may be wrong. Alright, now let's continue first by knowing that this is our fracture toughness. Alright, anything beyond that is considered unacceptable. Alright, so this system right now is under a certain stress. Alright, and this stress is being relayed over here. This is the stress tensor, if you remember. As you can see, if you want to find the principal stress, because we know that in the principal stress, sigma 1, sigma 2, and sigma 3, sigma 1 is the largest tensile stress, and we want to find it. Alright, and we are actually given one principal stress that is 200 MPa, and we need to find the other two. Alright, so we don't know whether this is sigma 1 or 2 or sigma 2 or sigma 3, we don't know. Alright, and we also cannot find in terms of this form. It's because if the use in terms of the so-called classic method of taking this minus away the principal stress, and then you solve their determinant, you can solve it. But however, they are in terms of 0 over here. Alright, so in fact, okay, you can actually solve it. Sorry. You can actually solve it, but however, it takes a long time. Alright, it takes a long time. So therefore, the purpose over here is already they actually give you this thing. So how do you use this and information on this to find your principal stress? And this is where we are coming from. And please note that we can also use this long method. Alright, and then find the determinant. Alright, so do not be so-called confused by me. I don't know what the hell am I talking about. Yeah, so this method can be used, but it's a long method. So that's why we often use we use this information to find the invariants, and then eventually we can solve it. So this is what our approach is, and therefore let's start. Therefore we will use this page. If you remember, take note of all this this one over here, because I cannot highlight. Hold on. Yeah, so we take this stuff. Alright, these are the terms that we need to sub it in. Alright, and therefore when we take it out, we'll have it over here. Alright, these are all the things that we take it out. Alright, and based on these things, this equation that we have been using, we can actually sub it in. Alright, instead of doing the long method of the sigma, and then you find the determinant, which is very long. So we can actually use this method to find, which is a much simpler way. Alright, and therefore to start, we'll need to be able to identify the sigma 1, 1, 1, 2, 1, 3 and things like that. Alright, because these are all in terms of that stuffs. Alright, need to do that. Alright, so therefore when you do that, alright, so sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. So it's 500 plus 0 plus 0, right? Because sigma 1, 1, sigma 2, 2 and sigma 3, 3 I would assume you know. So it's 500 plus 0 plus 0 goes to 500. Alright, and likewise you can apply all this stuff into the other stuff. Alright, you can just do it yourself, because I'm just conveying how do we do it, and yeah. So after which, when you have this, the answer will be minus 22 times 10 to the power of 4. Alright, for this case, and we have minus 56 times 10 to the power of 6. Alright, later you will know why, because when you do sigma 1 times sigma 2, 2 for example, alright, this is so sigma 1 times sigma 1, 2, 2 is actually 0. Alright, and then sigma 1 times sigma 3, 3, because this is also 0, this will become 0. Sigma 2, 2 times sigma 3, 3 is also 0, and the rest is calculating also over here. Same thing as for this one. Alright, most probably this one also, I don't know, but maybe not for this one, but anyway, you can just apply all this stuff into here. You should get all these values. Alright, you just sub it in only, and once you get this value, then you can just simply sub it in individually into this portion over here, and your I2 over here, and your I3 over here. Okay, see, we have all the I1, I2 and I3 sub into this equation. Alright, you can take a second to look. With this thing, then you can straight away solve for these roots. Alright, you can, one way is that because they actually given you one principal stress is 200 MPa. Alright, you can just sub it in. Alright, when you sub it in, factorize it out over here. Alright, so how you factorize is that you divide everything. This is the function that I've shown you over here. Alright, this is the whole equation that we have derived. It's also being rewritten over here. Okay, so over here. So you can just divide by stress minus 200, and then eventually you will get something like this. Alright, and why is it stress minus 200 is because if one root is 200, this means this is the root actually. So if this is 200, then we must have a minus 200 in order for this to be equals to 0, if you still remember. But this is a long chunk of method, because once you do this already, you still need to apply the quadratic formula all the way up to here to get 700 and minus 400. Alright, this is a long chunk, so that's why you can advise you to get a calculator. Once we calculated it, for me I use calculator, and therefore and I also know the answer, and therefore these are the stuff. Alright, and we're gonna sort which one is 1, which one is 2 and which one is 3, right? Because sigma 1, sigma 2 and sigma 3 for the principal stress, and we said that sigma 1 is the largest value, and sigma 3 is the lowest value, and therefore this will be 700 over here, 200 and minus 400. Alright, as you can see, smallest, this is the biggest, this is the medium one. Alright, so therefore I know my largest stress, principal stress is 700, that is pulling over at this direction in order to rip the crack apart, alright, or extend the crack. So therefore this is that. Also, that this may sound apparent to you that this is tensile stress, but you also need to know that this is applying in this direction, and therefore pulling this crack apart. So somewhat tearing this crack apart. You need to understand why do we take this direction, because in tests they don't actually tell you to do that. You need to know. Alright. Therefore, since we know that sigma 11 is equals to 700 MPa, then we can sub in back into this equation. Alright, this equation is to find our fracture toughness. Alright, this fracture toughness is given for the material, so we have to use this formula to find whether will we exceed this, and therefore I'll just simply apply 700 MPa times pi times A. But however, we are not given any values for A. Alright, how can we do about this? Because 25 MPa is over here, so actually my fault is that we actually keen to find A. Alright, we actually want to find what is the crack length that is allowable for our distress. Anything larger than this crack length will be unacceptable. Alright, this is our very objective, but I don't know what the hell am I doing just now. So sigma 11 is equals to MPa, as we know, so we'll just stop it in over here. Alright, and then so therefore this is just 700 times square root pi A, and then you should rearrange. It's just simple math, because 700 is in terms of MPa, and the fracture toughness is also MPa, so we just simply write this equation over here. Then therefore I'll just divide everything by 700. Alright, and then we remove the square root to be over here, and then we divide the whole thing by pi. Alright, so therefore you will get 0.38 millimeter. Okay, in case that you may forget, I'll just leave the answer over here as 0.000374 meter. So in order to change millimeter, we'll divide by 1000, and therefore what we have is 0.37 millimeter. Alright, and therefore this is the answer. So this crack length over here is 0.37 millimeter. Anything greater than this crack length, alright, when you apply this force over here, you're gonna actually pull this apart. In other words, if your crack length is smaller than this thing, then you can allow, because the stress applied will not propagate this crack itself, and therefore you'll always be up to the size. You'll always be here, and that's all it is. Alright, so I hope that this is a pretty clear example, and I shall see you in the next video for similar questions.